Good day everyone, I am Mimi Marta binti Jamilun and I will begin our presentation by introducing copper sulfide ores, their importance and role of the CYMET process as a sustainable alternative to traditional smelting. Copper is commonly extracted from sulfide ores such as chalcopyrite, chalcocite, bornite, and covellite. These ores are abundant and serve as the primary source of copper worldwide, typically occur in porphyry copper deposits, often associated with minerals like pyrite and sphalerite. Copper sulfide ores require complex extraction methods as the copper is tightly bound within sulfide minerals, making direct hydrometallurgical treatment difficult without prior oxidations or bioleaching. The properties of copper. Copper is a transition metal known for its excellent electrical and thermal conductivity, corrosion resistance, and recyclable. It is essential in electrical applications, construction, and renewable energy systems. In electrical applications, copper is used in wires, motors, and electronics in construction. It is used for roofing and plumbing. Meanwhile, for renewable energy systems, copper is important in electrical vehicles, solar panels, and wind turbines. Next, importance of the CYMET process. Traditionally, copper sulfide ores are processed using pyrometallurgical smelting, which involves high energy consumption, more than 1,200 degrees Celsius, emissions of SO2, sulfur dioxide gas contributing to acid rain, production of slag and other solid waste. The CYMET process, developed by Cytec Canada, offers a hydrometallurgical alternative to smelting. It uses chloride leaching and solvent extraction electrowinning to extract copper under milder conditions and lower environmental impact. Some of the key advantages are it operates at lower temperatures between 80 to 100 degrees Celsius, no SO2, sulfur dioxide emissions compared to smelting, allows recovery of valuable byproducts, iron and sulfur, can process low-grade ores and mine tailings, supporting sustainability. The CYMET process is important because it supports cleaner copper extraction and enables recovery from lower-grade ores, aligning with modern sustainability goals in metallurgy.
Assalamualaikum and hello, my name is Norisha. Now I will explain the process flowsheet for the CYMET process. First one is the leaching stage. In this step, the copper sulfide ore is mixed with an ammoniacal carbonate solution in the presence of oxygen. Copper is then dissolved from the ore, forming a complex ion called CuNH3 2+. This solution is known as the pregnant leaching solution or PLS. Impurities and solid residues such as sulfur are separated before moved to the next stage. Next is the regeneration stage. Here, the used ammonium carbonate solution is broken down to recover ammonia and carbon dioxide gases. These gases are then recycled back into the leaching process, so the same reagent can be reused. At the same time, other metals like iron, zinc, and lead can be removed from the solution through chemical or electrochemical methods. This helps to purify the solution and make the process more sustainable and cost-effective. Finally, the electrowinning stage. In this stage, the purified copper-rich solution goes through electrolysis. Copper ions are attached to the cathode where they are reduced to form solid metallic copper. At the anode, where water is oxidized to produce oxygen gas. This process gives us high purity copper metal and also regenerates part of the electrolyte for reuse. So, in summary, the CYMET process consists of 3 connected steps, which is leaching the soft copper from the ore, regeneration, recycle the chemicals, and electrowinning produce pure copper metal. Overall, it's a clean and efficient process that supports sustainable copper extraction. Now let's look at the main reaction equations for each stage. For leaching, copper sulfide reacts with ammonia, oxygen, and water to form soluble copper complex ion. The main reaction is CuS plus 8NH3 plus 1/2 O2 plus H2O become CuNH3 4 2 plus SO4 2 minus plus 2NH4 plus. This reaction dissolves copper into solution while leaving impurities behind. For regeneration, the ammonium carbonate solution decomposes to release ammonia and carbon dioxide gases. The equation is NH2 CO3 become 2NH3 plus 2 CO2 plus H2O. These gases are captured and recycled back into the leaching system to maintain reagent balance and reduce waste. Lastly, for electrowinning, copper ions are reduced to solid copper metal at the cathode, while the oxygen gas formed at the anode. The reaction R for cathode is Cu2 plus 2 electron negative. It becomes Cu, and then for anode, 2H2O become O2 plus 4H plus 4 electron negative. This stage completes the recovery of high purity copper. In summary, all these reactions are connected. Leaching dissolves the copper, regeneration restores the reagent, and electrowinning produces the final metal. Together, they form an efficient closed-loop system that minimizes waste and improves sustainability in copper production.
Hi, I'm Kwaji-san and I'll be presenting the unit processes and steps involved in CYMET process. So there are two stages in CYMET process, which includes the upstream processes and downstream processes. For upstream processes, they are all preparing and leaching stage, which include concentrate preparation, slurry formation, and leaching process, where in copper recovery and reagent regeneration stage, there are solid liquid separation, which is the solvent extraction, copper recovery, oxidant regeneration, and sulfur and effluent treatment. The mixed sites of run-of-mine ore will be undergo combination process, which it consists of crushing, grinding, milling, followed by classification process. And the purpose of combination is to remove the cross particles, reduce the particle size, and this will increase the exposed surface area of the ore to the following process, and this will ensure the better reagent contact during leaching process. So the finely ground concentrate from combination step will then sent to the slurry formation. In CYMET process, there are two options to produce slurry, which is the option 1, mix with water, then only mix with the chloride leaching solution, where the second one is directly mixing with the leaching reagent. So for the first option, which is mixed with the water first, this will help in controlling pulp density for better handling, less corrosion, and prevent early reaction, where when we directly mix the ground concentrate with the leaching solution, this will produce the faster reaction, simple setup, but it is more corrosive and harder to control. After that, we'll process to the leaching process. So in leaching process, the finely ground concentrate with the chloride leach solution will be fit into the leaching reactor, and then this will produce the pregnant leaching solution, which contain the copper ion and the residue. The residue here is the sulfur. Alright, so the pregnant leaching solution, which includes the dissolved copper ions in liquid form, and also the solid residue, which is the sulfur, gangue, and unreacted mineral, will then sent to the solvent extraction. So in this step, there are two ways to separate solid and liquid, which is the solid settling and also final separation and washing. This will produce the clarified PLS, and the clarified PLS will then sent to copper recovery process. There are two options to recover copper, which includes hydrogen reduction and electrowinning. In hydrogen reduction, copper chloride will reduce by hydrogen gas to produce metallic copper powder and also hydrochloric acid, which can be reused again, where in electrowinning, the PLS solution will fit into the electrolytic cell with the chloride media, and the cathode used is the copper metal, where at the anode, the pure copper metal will be produced, and the medium here is the copper-rich electrolyte, which is the PLS solution. Right after copper is recovered from pregnant leaching solution, we're going to regenerate oxidant, which is ferric chloride, FeCl3, from FeCl2, which is the ferrous chloride, that reduced during the leaching process. So there's two ways. First one will be the electrochemical oxidation done during copper electrowinning, and the second way is chemical oxidation, which is done in an oxidation tank, and the regenerated ferric chloride will recycle back to leaching reactor and form a closed loop. And after that, we're going to recover sulfur. Sulfur is a solid residue, so we can filter it out, melt it again and soak as byproduct, or we can undergo the oxidation and hydration process to produce the sulfuric acid. After that, we're going to treat effluent and tailings, so we need to make sure that the chloride solution and tailings water are neutralized to discharge safely. So the treatments here will be neutralization by using the lime or limestone, or the evaporation and crystallization to recover chloride. And also, we're going to recycle and treat water back to process to minimize the freshwater use.
Assalamualaikum. My name is Marina. As for my part, which is the critical analysis of a sustainability challenge in the CYMET process. The first one is the energy consumption, which is significant energy requirement for grinding, leaching, and electrowinning. The second one is the hydrogen production energy intensity in the reduction pathway, and also the thermal energy demands for maintaining reaction temperature. The second one is reagent management, corrosive nature of chloride media requiring specialized materials, potential ammonia volatilization in ammoniacal system, and also reagent losses in solid residue and effluent streams. The last one is the waste management. The waste management is in-house handling and stabilization of elemental sulfur in tailings, management of chloride-containing effluents, and also treatment and disposal of chem mineral and processed residue. Next, we have a potential improvement and innovation. In this part also, we have classified into three, which is energy efficiency, process optimization, and also environment performance. As for the first one, which is energy efficient, we have integration of renewable energy sources for electrical requirement, heat recovery system from exothermic reaction, optimization of particle size distribution to reduce screening energy, and also advanced reactor designs for improved heat transfer. As for the second part, which is process optimization, which is we have development of corrosion resistant matrix and coating, advanced control system for reagent optimization, integration of real-time monitoring and process analytics, hybrid processing routes combining the best feature of different system. So that is for process optimization. As for the environment performance, we have carbon capture and utilization from process streams, and then we have biodiversity protection in tailings management areas, the community engagement and environmental monitoring programs, and also we have life cycle assessment integration for continuous improvement. As for the conclusion, the CYMET process represents a transformative approach to copper extraction, effectively addressing the critical environmental limitation of traditional smelting by operating at moderate temperature through hydrometallurgical principles, which is it eliminates SO2 emission, a major environmental achievement, and fixed sulfur as a manageable and sellable byproducts. It is a closed loop design ensures to minimal reagent consumption and waste generation while offering operational flexibility through multiple copper recovery pathway. So this process also not only delivers high purity copper but also demonstrates a strong strong alignment with the principles of green metallurgy and sustainable resource management. As a global copper demand surge with the clean energy transition, the CYMET process stands as a viable, responsible alternation, proving that the metal extraction can be both economically sound and also environmentally conscious. It sets a new benchmark for the future of copper production, where efficiency and sustainability operate in concert. So that's all from our group. Thank you.